Last time we presented the critical section problem and focused on how race condition can happen when multiple concurrent processes share data. And then we examined several tools that address critical section problem. For example, we examined the memory barriers, and then we discussed about Mutex locks, semaphores, and monitors. We also discussed some challenges in designing applications such as liveness hazards like the deadlock. So in this topic, the objective is to explain the different problems or the several classic synchronization problems. So we will discuss about the different synchronization examples. So our objective is to explain the bounded buffer, which is part of the outline of this topic that we will discuss. We will explain the bounded buffer synchronization problem, the readers-writers problem, and the Dining-Philosophers problem. And then we will try to describe specific tools used by Linux and Windows to solve process synchronization problem. So those are the things that we are going to discuss. So among the classical problem used to test newly proposed synchronization schemes are the following. So they are made up of three classical problems of synchronization, namely number 1, bounded buffer problem, number 2, readers and writers problem, and number 3, Dining-Philosophers problem. Now in bounded buffer problem, which was introduced in our last topic, it was commonly used to illustrate the power of synchronization primitives. And in this example, the producer and consumer processes share the following data structure. So there was an integer n, which is the buffer where each can hold one item. And then we have a semaphore mutex, which is initialized to the value of 1. And then we have a semaphore empty, which was initialized to the value of n, or the number of buffer. And then the semaphore full, which was initialized to the value of 0. So we assume that the pool consists of n buffers, which are capable of holding one item. And the mutex binary semaphore provides mutual exclusion for accesses to the buffer pool and is initialized to the value of 1. And the empty and full semaphores count the number of empty and full buffers. The semaphore empty is initialized to the value of n, and the semaphore full is initialized to the value of 0. So this is the structure of the producer process, where the code for the consumer process is shown, and we can note that the symmetry between the producer and the consumer, and we can interpret this code as the producer producing full buffers for the consumer, or as the consumer producing empty buffers for the producer. This one is the structure of the consumer process. So as I have said, the structure of the producer interprets as the producer producing full buffers. So we have a signal full here. And then for the consumer process, the consumer is producing an empty signal buffer for the producer. So the next one is what we call the readers-writers problem. Suppose, for example, that a database is to be shared among several concurrent processes. And some of these processes may want to read the database. So the others may want to update. For example, they want to read and write the database. So we distinguish between these two types of processes by referring to the former as the readers and to the latters as the writers. So the readers, they can only read the dataset, but they do not perform any updates. But the writers, they can both read and write. So the problem is, obviously, if two readers access the shared data simultaneously, no adverse effects will result. However, if a writer and some other process, either a reader or a writer, access the database simultaneously, problems may ensue. And to ensure that these difficulties do not arise, so we require that the writers have exclusive access to the shared database while writing to the database. And this synchronization problem is called or referred to as the readers-writers problem. Since it was originally stated, it has been used to test nearly every new synchronization primitive. So the readers-writers problem has several variations and all involving priorities. The simplest one, referred to as the first readers-writers problem, requires that no reader be kept waiting unless a writer has already obtained permission to use the shared object. So in other words, no reader should wait for other readers to finish simply because a writer is waiting. And the second writers problem requires that once a writer is ready, the writer performs its write as soon as possible. In other words, if a writer is waiting to access the object, no new readers may start reading. So the solution to either problem may result in starvation. And in the first case, writers may starve. In the second case, readers may starve. For this reason, other variants of the problem had been proposed. So next, we present a solution to the first readers-writers problem. So in the first solution to the first readers-writers problem, the readers processes share the following data structure. So this is the data structure. The binary semaphores mutex and read-write mutex or RW mutex are initialized to 1. The read count is a counting semaphore initialized to 0. And the semaphore RW mutex is common to both reader and write processes. The mutex semaphore is used to ensure mutual exclusion when the variable read count is updated. And the read count variable keeps track of how many processes are currently reading the object. So the semaphore RW mutex functions as a mutual exclusion semaphore for the writers. It's also used by the first or last leader that enters or exits the critical section. And it is not used by readers that enter or exit while other readers are in their critical sections. So this is the code to illustrate the structure of a writer process. So the code for a reader process is shown here, and note that if a writer is in the critical section and n readers are waiting, then one reader is queued on RW Mutex and n-1 readers are queued on Mutex. So this is the illustration. Also observe that when a writer executes signal RW Mutex, we may resume the execution of either the waiting readers or a single waiting writer. The selection is made by the scheduler. So the readers-writers problem and its solutions have been generalized to provide reader-writer locks on some systems. Now for the next problem, we consider, for example, in the figure, we can consider an n number of philosophers sit around a table with a bowl of rice in the middle. So we consider 5 philosophers who spend their lives thinking and eating. So the philosophers share a circular table surrounded by 5 chairs and each belonging to one philosopher. So in the center of the table is a bowl of rice and the table is laid with 5 single chopsticks. When a philosopher thinks, she does not interact with her colleagues. From time to time, a philosopher gets hungry and tries to pick up the 2 chopsticks that are closest to her. So the chopsticks that are between her and her left and the right neighbors. So as we can see from the illustration, obviously, a philosopher may pick up only 1 chopstick at a time. So she cannot pick up a chopstick that is already in the hand of a neighbor. So when a hungry philosopher has both her chopsticks at the same time, she eats without releasing the chopsticks. And when she is finished eating, she puts down both chopsticks and starts thinking again. So the Dining-Philosophers problem is considered a classic synchronization problem. Neither because of its practical importance nor because computer scientists dislike philosophers, but because it is an example of a large class of concurrency control problems. And it is a simple representation of the need to allocate several resources among several processes in a deadlock-free and starvation-free manner. So one simple solution is to represent each chopstick with a semaphore. So a philosopher tries to grab a chopstick by executing wait operation as shown in this algorithm, and then she releases her chopsticks by executing the signal operation on the appropriate semaphores. Thus, the shared data are the following. So where all the elements of chopsticks are initialized to 1, in this case, the structure of philosopher I is shown here. And although this solution guarantees that no 2 neighbors are eating simultaneously, it nevertheless must be rejected because it could create a deadlock. So that is the problem with this algorithm. Suppose that all 5 philosophers become hungry at the same time and each grabs her left chopstick. All the elements of chopstick will now be equal to 0. And when each philosopher tries to grab her right chopstick, she will be delayed forever. And several possible remedies to the deadlock problem are the following. So the first one is to allow at most 4 philosophers to be sitting simultaneously at the table. Number 2, allow a philosopher to pick up her chopsticks only if both chopsticks are available. And to be able to do this, she must pick them up in a critical section. Third, we use an asymmetric solution. That is, an odd-numbered philosopher picks up first her left chopstick and then her right chopstick, whereas an even-numbered philosopher picks up her right chopstick and then her left chopstick. So in this particular example, as a solution to the Dining-Philosophers problem, each philosopher I, for example, invokes the operation pick up and put down function in the following sequence. So when the Dining-Philosopher pick up, the next case is to eat. And after that, the Dining-Philosophers put down. So this is a solution. There will be no deadlock because if someone picks up, someone will eat. And after that, it will put down the chopstick. But the problem with this is starvation is possible. So for Windows and Linux operating systems, they describe the synchronization mechanisms where in these two operating systems, they provide good examples of different approaches to synchronizing the kernel. And as you will see, the synchronization mechanisms available in these systems differ in subtle yet significant ways. For example, in synchronization in Windows, the Windows operating system is a multi-threaded kernel that provides support for real-time applications and multiple processors. So when the Windows kernel accesses the global resource on a single processor system, it temporarily masks interrupts for all interrupt handlers that may also access the global resource. And in a multi-processor system, Windows protects access to global resources using spin locks. This is used for multi-processor systems to protect the access to this global resource. So although the kernel uses spin locks only to protect shortcode segments. So furthermore, for reasons of efficiency, the kernel ensures that a thread will never be preempted while holding a spin lock. Now, for thread synchronization outside the kernel, Windows provides dispatcher objects. And this, using a dispatcher object, threads synchronize according to several different mechanisms, including mutexes or mutex locks, semaphores, events, and timers. So what are events? Events are defined as an event which acts much like a condition variable. So similar to condition variable, but they can notify a waiting thread when a desired condition occurs. So finally, timers are used. So these timers are used to notify one or more than one thread that a specified amount of time has expired. Meanwhile, dispatcher objects may be in either a signal state or a non-signal state. So an object in a non-signal state is not available, and a thread will block when attempting to acquire the object. While when an object is in a signal state, the thread will not block when acquiring the object. So this is an illustration of the state transition of a mutex lock dispatcher object. So in this relationship, we can see that the relationship exists between the state of a dispatcher object, a mutex dispatcher object, and the thread blocks. And each state changes from ready to waiting. So from ready, it becomes waiting. And the thread is placed in a waiting queue for that particular object. So when the state for the dispatcher object moves to signaled, from the non-signal, it moves to signaled, the kernel checks whether any threads are waiting on the object. If so, the kernel moves one thread or possibly more from the waiting state to the ready state where they can resume executing. So the number of threads the kernel selects from the waiting queue depends on the type of dispatcher object for which each thread is waiting. The kernel will select only one thread from the waiting queue for a mutex, since a mutex object may be owned by only a single thread. And for an object or event object, the kernel will select all threads that are waiting for the event. For Linux synchronization, prior to version 2.6, Linux was a non-preemptive kernel, meaning that a process running in kernel mode could not be preempted. So even if a higher priority process became available to run. However, now, the Linux kernel is fully preemptive. So a task can be preempted when it is running in the kernel. And Linux provides several different mechanisms for synchronization in the kernel. As most computer architectures provide instructions for atomic versions of simple math operations, the simplest synchronization technique within the Linux kernel is the atomic integer, which is represented using the opaque data type atomic CT. As the name implies, all the math operations using atomic integers are performed without interruption. And to illustrate, we have an example here of an atomic variable, which is the type for atomic integer. When this atomic variable is being executed, as was defined earlier, it cannot be preempted. So it has to be computed without interruption. So the atomic operation, when this atomic variable is used, the operation should be performed without interruption. So this is an example of the atomic operation and the effect as displayed in this particular figure. So the synchronization methods discussed in the preceding part of this lecture pertains to synchronization within the kernel, and they are available only to kernel developers. However, the POSIX API is available for programmers at the user level, and it's not a part of any particular operating system kernel. So this is not for Windows or for Linux. And of course, it must ultimately be implemented using tools which are also provided by the host operating system. So in this section, we will cover the mutex locks, semaphores, and condition variables that are available in the pthreads and POSIX API APIs. And these APIs are widely used in Unix, Linux, and Mac OS systems. For the POSIX Mutex locks, it represents the fundamental synchronization technique used with pthreads. So in this example, we can see that a mutex lock is used to protect critical sections of the code. So for example, a thread acquires the lock before entering a critical section, and then it releases it upon exiting the critical section. So the pthread here uses the pthread mutex init function, where the first parameter here is a pointer to the mutex. So this is a pointer at mutex. This is a pointer to the mutex. And then by passing the null value as a second parameter, we are initializing the mutex to its default attributes. So this is illustrated in this particular code. Then the mutex is acquired and released with the pthread mutex lock function. So if the mutex lock is unavailable when this pthread mutex lock is invoked, the calling thread is blocked until the owner invokes pthread mutex unlock function. And these are the following codes which illustrates protecting a critical section with mutex lock. And all of these mutex functions return a value of 0 with correct operation. But when an error occurs, these functions return a non-zero error code. For POSIX Semaphores, many systems that implement pthreads also provide semaphores. Although semaphores are not part of the POSIX standard and instead belong to the POSIX Sem extension, POSIX specifies two types of semaphores, namely named and unnamed semaphores. Fundamentally, the two are quite similar, but they are different in terms of how they are created and shared between processes. Because both techniques are common, so we discuss both here. So the function semopen, as you can see from when we create and initializing the semaphore for the POSIX named semaphores, the function semopen is used to create and open a POSIX named semaphore. And in this instance, we are naming the semaphore sem, the oCreate, this one, the oCreate flag, which indicates that the semaphore will be created if it does not already exist. Additionally, the semaphore has a read and write access for other processes via the parameter 0666 and is initialized to 1. So the advantage of named semaphores is that multiple unrelated processes can easily use a common semaphore as a common semaphore as a synchronization mechanism by simply referring to the semaphore's name. So for the unnamed semaphores of POSIX, so the seminit function, as you can see from here in the illustration, the unnamed semaphore is created and it uses the initialization seminit function, which is passed 3 parameters. And what are these parameters? The first parameter is the pointer to the semaphore, which we call it @sem. And then the second one is a flag indicating the level of sharing. In this case, it's a 0 flag. And then the third one is the semaphore's initial value, which in this case is 1. So in this example, by passing the flag 0, we are indicating that this semaphore can be shared only by threads belonging to the process that created the semaphore. So if we supplied, for example, a non-zero value, we could allow the semaphore to be shared between separate processes by placing it in a region or shared memory. So in addition, we initialize the semaphore to the value 1. POSIX also has condition variables, and these condition variables in pthreads behave similarly to those described in the last section. However, in that section, condition variables are used within the context of a monitor. So recall that it provides a locking mechanism to ensure data integrity. So condition variables in POSIX uses pre-threads, and it uses the data type pthread condt variable data type, and they are initialized using the pthread condition init, this one, okay? And our condition variable, this condition variable creates and initializes the condition variable as well as its associated mutex lock. So the pthread condition weight here that we can see is used for waiting. So this one, this is used for waiting on a condition variable. And here in the following code, it then illustrates how a thread can wait for the condition where A will be equal to B to become true using a pthread condition variable. So the mutex lock associated with the condition variable must be locked before the pthread condition wait function is called, since it is used to protect the data in the conditional clause from a possible race condition. And once this lock is acquired, the thread can check the condition. But if the condition is not true, the thread then invokes pthread condition wait, passing the mutex lock and the condition variable as parameters. For Java synchronization, we have a set of synchronization features such as Java monitors, reentrant locks, semaphores, and condition variables. So for Java monitors, so in every Java object, each Java object is associated with a single lock. So Java provides a monitor-like concurrency mechanism for thread synchronization. And it is illustrated in this figure using the mechanism with the bounded buffer class. This implements a solution to the bounded buffer problem wherein the producer and the consumer invoke the insert and remove methods respectively. And every object in Java has associated with it a single lock, no? as it was described here. Every Java object is associated with a single lock. So when a method is declared to be synchronized, calling the method requires owning the lock for the object. And we declare a synchronized method by placing the synchronized keyword in the method, such as within the insert and remove methods in the bounded buffer class. So continuing with the Java synchronization, where each object has a wait set, so when a thread calls for the wait function, it does the following. As was illustrated here, number one, it will release the lock for the object, and then the state of the thread is set to be block. And then for the number 3, the thread is placed in the wait set for the object. So the simplest locking mechanism available in the API for Java is the reentrant lock. And in many ways, they are similar to Mutex lock. They also act like the synchronized statement which was described earlier. So a reentrant lock is owned by a single thread and is used to provide mutually exclusive access. That's why it's similar to Mutex locks. However, the reentrant lock provides several additional features such as setting a fairness parameter, which favors granting the lock to the longest waiting thread. So we can recall that the specification for the Java virtual machine does not indicate that threads in the wait set for an object lock are to be ordered in specific fashion. So a thread acquires a reentrant lock by invoking its lock method, and if the lock is available, or if the thread invoking lock already owns it, which is why it is termed reentrant lock, it assigns the invoking thread lock ownership and returns control. But if the lock is unavailable, the invoking thread blocks until it is ultimately assigned the lock when its owner invokes the unlock. For Java semaphores, Java API also provides a counting semaphore, and the constructor for the semaphore appears as semaphore int value, where the value here specifies the initial value of the semaphore, which is a negative value, can be allowed. So the acquire function method, which you can see from here, allows or throws an interrupted exception here if the acquiring thread is interrupted. So this is an illustration of the semaphore for mutual exclusion. Notice that we place the call to release in the bottom, in the finally clause, to ensure that the semaphore is released. For Java condition variables, which is the last utility for Java API, just as the reentrant lock is similar to Java's synchronized statement, condition variables provide functionality similar to the wait and notify methods. Therefore, to provide mutual exclusion, a condition variable must be associated with a reentrant lock. So we create a condition variable by first creating a reentrant lock, and then invoke it using the new condition method, which returns a condition object representing the condition variable for the associated reentrant lock, and this is illustrated in this example. So once the condition variable has been obtained, we can invoke its await method and signal method, which function in the same way as the wait and signal commands we discussed earlier. Now, with the emergence of multi-core systems, which has increased pressure to develop concurrent applications that take advantage of multiple processing cores. However, concurrent applications present an increased risk of race conditions and liveness hazards such as deadlock. So traditionally, techniques such as mutex locks, semaphores, and monitors have been used to address these issues. But as the number of processing cores increases, it becomes increasingly difficult to design multi-threaded applications that are free from race conditions and deadlock. So in this section, we explore various features provided in both programming languages and hardware that support the design of thread-safe concurrent applications. So we have transactional memory, OpenMP, and functional programming languages. So we'll try to study those one by one. So first, for the transactional memory, in computer science, ideas from one area of study can be used to solve problems in other areas. So the concept of transactional memory originated in the database theory. For example, yet it provides a strategy for process synchronization. A memory transaction is a sequence of memory read and write operations that are atomic. When we say atomic, that means it cannot be interrupted or uninterrupted. So otherwise, if all operations in a transactions are completed, the memory transaction is committed. So otherwise, the operations must be aborted and rolled back. So the benefits of transactional memory can be obtained through features added to programming language. So for an example, suppose we have a function update. So this is our function update, which modifies the shared data. So we acquire using the acquire function, and then it modifies the shared data. So traditionally, this function would be written using mutex locks using the following semaphores. So we use the acquire function and then the release function. However, using synchronization mechanisms such as mutex locks and semaphores involves many potential problems, including deadlock. And then as the number of threads increases, traditional locking doesn't scale as well because the level of contention among threads for lock ownership becomes very high. So as an alternative to traditional locking methods, these new features that take advantage of transactional memory can be added to programming language. So in this example, suppose we add the construct atomic S, which ensures the statements in S are executed atomically. So this allows us to write or to rewrite the void update function as follows. So we just use the function atomic. So instead of using the acquire and release, we can use the atomic function. So the advantage of using this mechanism rather than locks is that the transactional memory system, not the developer, is responsible for guaranteeing atomicity. So additionally, because no locks are involved, deadlock is not possible. And furthermore, a transactional memory system can identify which statements in atomic blocks can be executed concurrently, such as concurrent read access to shared variable. So it is possible for a programmer to identify these situations and use a reader-writer lock, but the task becomes difficult as the number of threads within an application grows. So this transactional memory can be implemented in either software or hardware. So, as the name suggests, implements transactional memory exclusively in software where no special hardware is needed. So that is STM. If it is HTM, or hardware transactional memory, the code is inserted by a compiler and manages each transaction by examining where statements may run concurrently and where specific low-level locking is required. So in the HTM, it uses a hardware cache hierarchies and cache coherency protocols to manage and resolve conflicts involving shared data residing in separate processor cache. So for the OpenMP, we can recall that OpenMP includes a set of compiler directives and an API that supports parallel programming. So any code following the compiler directive pragma, this one is the pragma parallel, is identified as a parallel region and is performed by a number of threads equal to the number of processing cores in the system. So the advantage of OpenMP and the similar tools is that thread creation and management are handled by the OpenMP library and are not the responsibility of application developers. So along with the with its pragma parallel compiler directive, OpenMP provides the compiler directive pragma critical, which specifies the code region following the directive as a critical section and performed atomically. So in this way, OpenMP provides support for ensuring that threads do not generate race conditions. For functional programming languages, we all know that most well-known programming languages such as Turbo C, C++, Java, and C# are known as imperative or procedural languages. So imperative languages are used for implementing algorithms that are state-based. And in these languages, the flow of the algorithm is crucial to its correct operation. And state is presented with variables and other data structures. Of course, program state is mutable, as variables may be assigned different values over time. And with the current emphasis on concurrent and parallel programming for multi-core systems, there has been greater focus on functional programming languages, which follow a programming paradigm much different from the offered by the imperative languages. So the functional programming languages offer a different paradigm because of the procedural language which do not maintain states. And then the variables are treated as immutable and cannot change state. Okay? So there is an increasing interest in functional languages such as Erlang and Scala for their approach in handling data races. So the fundamental difference between imperative and functional language is that functional language do not maintain the state. So that is once a variable has been defined and assigned a value, its value is immutable. So it cannot change a state as discussed here, no? Because functional language disallow mutable state. They need not be concerned with issues such as race condition and deadlocks. So these are the several functions of synchronization examples that we have discussed here. The last parts are the alternative approaches to solving the critical section problem, include transactional memory, OpenMP, and functional language. So we describe all of this, and we shall continue with our next topic. But for now, we end this topic with this slide.